catch me at coffee if you want to ask lots of questions, and I'll put some material out there. Taking up too much time. One moment now. So I back slowly away.
So this one also works?
They should both work. Yeah.
That one seems to be out of battery. Okay. So does this working?
Yes.
Okay, good. Yeah, so I was going pretty slow for the first 3 lectures. And so I'm going to cheat, okay? So now I'm going to use
I
slides.
just want to say, Hung, I'm glad you were not going fast.
Okay, yeah, because I want also show you not just say this formalism, I also want to show you some applications so that you see some punchlines. And otherwise, some of you surely will ask me, where's the beef? So let me just give a brief summary of the what we discussed for the 3 lectures. Is that the emphasize that the classification of von Neumann algebras provide the classifications of general patterns of entanglement. And so the usual approach to entanglement, even for systems which you cannot factorize, then you can just introduce some regularization and still calculate the entropy, etc. That have generated many, many important insights, okay, have been very powerful. And this algebraic approach is complementary to this more usual approach, both conceptually and technically, which I have emphasized earlier. So they offer in some new perspectives and new tools. Okay, so in physics, we want to look at the system from all possible perspectives. Okay, so that will, because you don't know which perspective will lead to something completely new or some new avenue, etc. Okay, so we need to examine everything. And then finally, also I want to mention that the theory of von Neumann algebras is a very rich mathematical subject. And there's also a field called algebraic quantum field theory, which started in 1960s. People already recognized in the 1960s, the importance of algebraic, this von Neumann algebras for quantum field theory. And they have accumulated many, many nice results. Okay, so unfortunately, the physics community has been kind of ignoring those results for many years. So potentially there's many hidden treasures. Okay, sorry, I made some misprint here. Potentially many hidden treasures in those mathematics and in those old works of algebraic quantum field theories. And also to apply this kind of von Neumann algebras to thinking about the quantum gravity are just starting being explored. So potentially, maybe much can be learned. Okay. So today I want to tell you some examples, okay, which we can use this to try to understand some aspect of gravity. So before doing that, do you have any questions? Good. Mm-hmm. Okay, so just to remind you, the plan I had before is that, so this is the first part, and then I want to talk about the large M limit of the ADS CFT duality. Then I will talk about the, anyway, so we will see what we can do. Also remind you, our goal is that we want to understand, using the ADS CFT duality, understand how does such kind of geometric notions, like local regions, local degrees of freedom, causal structure, different notions of time, emerges in the G Newton goes to 0 limit. Okay, and we do this by examining what happens to the boundary CFT in the large N limit. So we want to understand the emerging physical and mathematical structures, say, of this angle to infinity limit. Okay. And so even though the discussion will be general, but it's always good to keep in mind some prototype example, say n for super Yang-Mills series with gauge group SUN. And so we take this n go to infinity. So now one key point to one immediate point is that when you consider the n go to infinity limit, the many states and operators, if you can consider, say, a family, say, of series with this parameter n, and if you, say, can track some states as you change n, and then the various states, the energy just go to infinity when you take n go to infinity, and then become, so defining such state in the n go to infinity limit become tricky, okay? So similarly with operators, say some operator dimension will go to infinity, etc. The interpret those operators in the large n limit also become tricky. So I want to, so the structure, because of this, and the structure, so we should look at those states and the operators which have well-defined large n limit, okay? And so for this reason, the structure of the Hilbert space and the operator algebras can undergo dramatic changes in the large n limit. And precisely is this kind of changes we want to understand, and because that will be responsible for this emergence of these space-time notions, okay, geometric notions in space-time. And so again, a philosophical analog is this the quantum field theory on the lattice, which we already mentioned a couple of times. So consider you put the theory on the lattice, and the lattice spacing is A, then you take L go to infinity, zero limit, you get the continuum theory. And so in the, say, suppose we consider the region, say, some right half of this lattice. And the Hilbert space, say, on the lattice, the Hilbert space factorized into the right part and the left part, okay? And then the algebra is type 1, okay? You have standard algebra for type 1. But then when you take A go to 0 limit, when you go to continuum limit, many states in this Hilbert space, their energy diverges, okay? Their energy diverge when you take A go to 0. And also some operator become singular when you take A go to 0. And then they just drop out, okay, in your continuum limit. So as a result, the Hilbert space and operator algebra structure in the continuum limit is very different, okay, for on the lattice. And for example, the H become non-factorizable, and that's emphasized earlier. Then the algebra become type 3-1. Okay, and also related to this change is that in this case there's no sharp light cone, and now of course when you go to continuum theory, we have sharp causal structure. Okay, so this is a philosophical analog to understand, say, maybe similar things happen in the large n limit. Okay. Good. So now let's examine what happens to the operator algebra in the large n limit. Again, we keep this equitable super Yang-Mills theory as a prototype example. So we say an operator have a sensible large n limit if its vacuum correlation function has a well-defined n go to infinity limit. Okay. Yeah, of course, the underlying assumption when I say an operator have a large n limit, first you have to be able to define this operator for all n. Okay, and then you look at the behavior of this operator, a correlation function of such operators in the vacuum. Okay, and then if their correlation functions have a n go to infinity limit, and then we say this operator has a well-defined limit. And so from the standard this large n story, and then the operators survives are the finite product of single trace operators. So the single trace operators, say in the Yang-Mills theory, are the operators say like trace f squared. Okay, so this is a single trace operator, or trace to the f4, etc. Okay, so this is another one. Okay, this is another one. So the important property in the Lagrangian limit is that if you normalize your Lagrange in the particular in the appropriate way, and the correlation function of such operators, say, is of order 1, okay, independent of n. So they have a well-defined limit, and when you go to infinity. And furthermore, if you look at the product, say, of many, say, single trace operators, and then you have some kind of losses, you have some kind of, what is that name? They all factorize into 2-point functions, okay, to the leading order in Lagrange. A weak contraction, yeah. Something like the weak contraction exists in the Lagrangian limit, so at the leading order, they just factorize into 2-point functions, and then suppressed by 1 over n, okay, suppressed by 1 over n. So at the leading order in Lagrange, again, all these correlation functions are given by order 1. Okay, again, it's well defined. Okay, it's well defined. So so those are the operators which survive. And then you can take the finite product of such operators, and then they form an algebra in the Lagrangian limit. So we can call them single trace operator algebra. So they just built from. So these are the building blocks, say, of your algebra. Okay, you just take the product of them. Yes?
Is the only way to obtain Wick factorization, i.e. generalized free fields, through a large n theory?
You can define a generalized free field in many different ways. A Lagrangian theory just one way. Yeah.
Oh, okay.
Yeah. You can just a generalized free field. You can just specify. You can just define it abstractly. You don't have to come from a Lagrangian theory.
Through the correlation.
Yeah. Right. Good. So so it turns out that this algebra have some key features. So first, so before one thing I also want to remember is this example of the coupled spin example we talked about last time. So remember this another example, we have two systems of n spins. Okay, we have L system and R system, which they are entangled. Okay, so and n goes to infinity. So here n is the number of spins. Okay. So in this case, we define the state depend on a parameter theta, which is the tensor product of all different phi theta. Okay. So keep in mind this example. Okay. So I want to put that there. And so the analog of the single trace operator here. So in that example, are the operators which you just flip the finite number of spins. Okay, and there is the operator which flip finite number of spins which survive in the n goes to infinity limit. And so it's an analog of the single trace operator here. So the key features here is that the operator algebra actually becomes state dependent. Okay, the operator algebra becomes state dependent. So again, that happens in that example. When you take the n spin goes to infinity. So remember we discussed that the algebra is just depend on the value of theta. So if theta is maximally entangled, then you have type 2-1. And for some other values of theta, you have type 3 algebras. So the algebra actually depend on the nature of the algebra actually depend on the state. Okay, and the same thing happening here. Okay, in the Lagrangian limit, we will find actually the algebra can become state dependent. So this is one key feature, and another feature is that they don't have counterpart in. Another feature we don't have counterpart in that quantum mechanics example is that the single trace operators at different time are allow independent. Okay, So let me now elaborate a little bit on this point. So let's just consider you have a standard quantum field theory, which you have a causal diamond. And now let's consider two Cauchy slices of this causal diamond. And now let's look at the operator algebra associated with these two Cauchy slices. So this blue one and this red one. So the operator algebra on the blue one, let's call it A1, and the one on the A2, on the red one, we call it A2. So in the standard quantum field theory, or at finite n, so this A1 algebra is completely equivalent to A2. It's because any operator, say, on this red slice, you can always express in terms of the Heisenberg evolution, in terms of the operator on the green slice, okay? So they can just be expressed in terms of each other. And so these two algebra are just exactly the same, okay? Just physically completely equivalent, okay? But in the large n limit, the algebra of, so now in the large n, we only need to keep the single trace operators, okay? It turns out the single trace operators, now the A1 and the A2 actually are independent of each other. Okay, so there are various ways to understand this. And one way to understand this is that when you take the large n limit, okay, when you take the large n limit, the Heisenberg evolution operator actually becomes ill-defined. It's because you have to define your Heisenberg evolution carefully. Because the Heisenberg evolution corresponding to expansion IHT. But the H, the Hamiltonian have the structure which is n times a trace something. Okay, so there's an explicit factor of n here. Okay, so this explicit factor n here making the definition of this operator very tricky when you take n go to infinity limit. Okay. And anyway, so heuristically say if you take a single trace operator on slice A2, and now suppose at the finite n you express them in terms of operator on A1, when you take n go to infinity limit, some of those operators on A1 will drop out. Okay, so and then if you only keep single trace operators, then they become independent. Okay. So this aspect will play a very key role in our discussion, even though it's a very simple point. And because of this reason, now the operator algebra at the different time slices are independent. And now this gives you a much richer algebraic structure. Okay, and also give you much richer set of algebras. Okay.
So it is no longer type 3, the single trace operator?
Yeah, I will talk about this point later. Yeah, indeed, the original type 3, that algebra is no longer relevant because many operators in that original algebra, they decouple. Right, so you have to reevaluate what is this algebra. Yeah, but they turned out still to be type 3, but different kind of type 3. Yeah.
Yes. Take a cross product with some other algebra and make them equivalent. Can they be made equal by taking a cross product at every time step?
No. Mm-hmm. Okay, good. So now let me say a little bit about the Hilbert space in the large n limit. So first let's talk about on the gravity side, which is relatively simple. So when you take a large n limit corresponding to the G-Newton goes to 0 limit on the gravity side. So on the gravity side, we just have the standard, in the G-Newton goes to 0 limit, the quantum states, there's some quantum states survive, have a sensible semi-classical limit, and that gives rise to the classical geometry. And then we can quantize around the classical geometry to obtain other quantum states, okay, excitations around the classical geometry. And so for example, let's say, let's denote the classical geometry chi, and then we can quantize all the matter fields, small perturbations, including metric around the chi, and then you get some Fock space. So to the leading order, say in the G-Newton expansion, you have a Fourier series, and then you can construct Fock space. And then by definition, the states in the same Fock space have energy difference, say order by G Newton to the power 0, which is order n to the power 0. And so energy differences for different for two kind of classical geometry, they differ by G Newton to the order -1, yeah, because they back rack to the geometry. So that's order n squared. Okay. So this immediately tells you that the Fock spaces for two different classical geometries, they don't overlap. So that means that the full Hilbert space, okay, of your quantum gravity, when you take the G Newton goes to 0 limit, actually splits into disconnected Fock spaces around different geometries. Okay. So this is the same analog as this angle to infinity example in this spin example. In the spin example, so if you have a finite n, then you have a Hilbert space of all possible states. Okay? But now when you take angle to infinity limit, and then for each different theta, now there's a Hilbert space for each theta. Okay, then the angle to infinity limit here, the Hilbert space is obtained by you act finite number of spins on this state. And then you will generate with the Hilbert space h theta. And different h theta, again, they don't overlap. Because in order to relate different theta, you have to rearrange infinite number of entanglement here. Okay, and that's, you don't have ideal proposal. Okay, and it's the same thing in the Lagrangian limit for the, yeah, here. Okay, so there's a corresponding boundary theory descriptions. So it's in the name of GNS Hilbert space. And the idea is very similar. So the Bach geometry should be considered as dual to some states on the boundary theory. And so we call such a state which dual to a classical geometry, say a semi-classical state. Okay, so these kind of states have well-defined angle to infinity limit, and they have very good properties, say including factorizations, etc. So now for semi-classical state psi, which dual to a Bach geometry, we can build a Hilbert space around it by acting finite product single trace operator on it. Okay, so exactly the way as we build the Hilbert space for this spin example. Okay, a spin example. And so this is normally called the GNS Hilbert space. Yeah, you can formalize this procedure mathematically, and this is called GNS Hilbert space. And so essentially the duality with the geometry implies that again in this kind of state, single trace operator satisfy some kind of Lagrangian factorization. Okay, and so that means that the GNS Hilbert space can be associated with the Gaussian theory because you have factorized two-point function at the leading order in 1 over n. So this GNS Hilbert can be described by a Gaussian theory of single trace operators. And yeah, so here we essentially just have a generalized free field theory for the single trace operators. And for the same reason as on the gravity side, and also in this simple spin example, and the different GNS Hilbert space don't overlap. Okay, because when you, to go between different semi-classical states require the infinite amount of energy. Okay. When you go to take angle to infinity. So to summarize, so the structure of the ADS-CFT duality has Lagrangian have the following feature. So you have geometry states on the CFT dual to some geometry, and then we should have an indication. In the Bach we have Fock space, and in the boundary we have this GNS Hilbert space, so they should be identified, because they should have one-to-one correspondence between the physical states. Okay. And then there's also one-to-one correspondence between the generalized free field, so those kind of single trace operator in the boundary theory with the free field in the Bach. So to the leading order in G Newton expansion in the Bach, we just have free Bach fields, and so they should have one-to-one abundance each other. So since we identified the Hilbert, GNS Hilbert space, and then the operator algebra acting on those space should also be identified. Okay, and so those algebra on the field theory side are generated by single trace operators, and this on the Bach side just generated by the Bach fields. So here is a cartoon picture for one semi-classical state. You have equivalence of the GNS Hilbert space and the Fock space, and also all the operator algebras here, they should be equivalent. And then you have some disconnected another Hilbert space corresponding to some other semi-classical states. Okay. And so I emphasize that this algebra is state dependent. Okay, just like in that spin example, the algebra is state dependent, and here, in principle, they are all state dependent because they act on different Hilbert space. Okay, even though it's generated by the same kind of single trace operators, but now they act on different Hilbert space, and so now the algebra becomes the state dependent. So this is a very important point. Yes.
Should those and the operator algorithms be flipped on the why?
Oh yeah. Sorry, yeah. They should be flipped. Yeah, that's right. Good. Thank you. Any questions on this? Yes.
So if you allow yourself to act with operators with more than a finite product of single trace operators, you can get between the different representations.
Yeah.
So you have a physical interpretation of how the operators that take you between these Hilbert spaces built between these different states.
So we don't know precisely. So now let's imagine you have a finite n, but n very large, or on the gravity side corresponding to G Newton very small, and then you have roughly equivalent picture, but now they are no longer precise Hilbert space anymore. They just become some collection of states. Okay, so those states they still are there. And now then you can have operator which to go from one space to another space. And such operator, they should have very large dimensions. And so say order n square, etc. The nature of such kind of operators depend on the details. So depend on the depend on psi 1, psi 2, etc. The only thing we can say in general, they should have order n square dimensions. Other questions? Okay, good. Okay, so now we are ready. So this concludes our discussion, a very quickly review of the ADS-CFT duality at large n. So now there's a trivial corollary from this statement, okay, from what I just said. So now let's just consider a Bach region. So consider causally complete the Bach region B. And so in the G Newton goes to 0 limit, then there's some kind of, the Bach is described by quantum field theory in the curved space-time. And then you can now look at the Bach field operator algebra, which I call Y tilde B in B, okay? And so as we mentioned before, so if you have a quantum field theory in the local region, then that should be type 3-1, okay? And this algebra should be a sub-algebra of the full operator algebra, say in your Fock space. Yeah, this Fock space, full Fock space algebra by definition is type 1, okay? And so this is a type 3-1 algebra, sub-algebra of that. And then, by definition, because of this correspondence between the m psi tilde and this single trace operator algebra on the CFT side, then that means in the n go to infinity limit, that there must be some emergent type 3-1 sub-algebra, which is a sub-algebra of the algebra acting on the GNS Hilbert space on the field theory side, which is identified with this Y tilde B. Okay, so there must be a one-to-one correspondence between them. Okay, so And the reason this is emergent because this is emergent in the gravity side when you take G Newton goes to zero limit. So this must be emergent in the angle to infinity limit. Okay, so angle to infinity limit, so you must have something, this kind of thing emerges. And so this is what we call the subalgebra subregion duality. Okay, so the general subregion in the block, you should be able to find the subalgebra in the field theory to describe it. Okay, and now the properties of such emergent type 3-1 algebras then should characterize the geometric closures such as horizons, times, and causal structures, etc. Okay, but of course the key is how you find this y. Okay, and so now I will talk about give you some examples and also to show how this works. Okay, how this works. Any questions on this? Yes.
So there is this famous story about inclusions of monomial algebras, so we can get fusion categories of bimodules and so on. Does it have it?
Yeah, they may have some applications here, but here I will not use those things. Yeah. Okay, good. So now I will talk about the example. So again, we go back to this internal black hole, which Juan talked about many times. Okay. Here I want now see how various geometric structure of the internal black hole emerges from the field theory. So yeah, you have seen this a picture many times. We have this internal black hole in ADS, and so this is supposed to do the thermal field double state, 2 copies of CFT in the thermal field double state. Okay, and so you may also consider this spin example as a toy example for this, and so this kind of entangled state we built between the left spin system and the right spin system. And maybe consider as some kind of thermal field double state. Okay. In particular, when theta equal to pi over 4, that's exactly a thermal field double state for temperature for infinite temperature. Okay. And so here the thermal field double state is labeled by a parameter beta, yeah, inverse temperature. And now, so here you have the boundary time is the CFT time. And this boundary time, you can naturally extend them into the block. Okay, then they become the Box-Schwarzschild time. Okay, but the Box-Schwarzschild time, they stop at the horizon. Okay, they stop at horizon corresponding to t equal to plus infinity and t minus infinity. Okay, and similarly for the left-hand side. Okay, so now it's an immediate puzzle. How do we describe this future and the past region? Because of the time, the available time run out, okay, on the boundary, okay. How do we describe the Kruskal time? Okay, the Kruskal time is the one can take you to the F and the past regions. Also, what would be the boundary descriptions of horizons and associated causal structure associated with this black hole? And also, as Juan also mentioned, say you can in principle have observers from the right and the left. They will jump in. They can meet there, okay? And how do we actually understand this kind of behavior, okay? Good. So we will try to understand those questions from this, using insight from this volume algebras. Okay. So first, let me just mention that actually the thermal field double picture due to a black hole actually only applies for temperature sufficiently large. So there's a so-called Hawking-Page transition. So if you have the only above the sufficiently high temperature, you are described by the black hole. And if the temperature is sufficiently low, and then actually described by the 2 copies of the ADS. And so in these 2 copies of ADS, each copy is excited a little bit with some kind of graviton gas inside each copy, and then you entangle those graviton gas. Okay, and this is very different from this connected geometry. So here is 2 connected geometry, or 2 disconnected geometry, and then you entangle degrees of freedom inside the geometry. Okay, and here you have two connected, here left and right, they're connected. Okay. Good. So at finite n, so the bounded operator algebra in the CFTR or CFTL is a type 1 von Neumann algebra. Okay, because this is the algebra for the full CFT. Okay, you have a full CFT entangled with a CFT to the left. So the full CFT algebra is always a type 1 algebra. And that algebra is state independent. Okay, you just have some full operator algebra for the right CFT or for the left CFT. Okay. But now in the Largier limit, as we mentioned, we should look at the algebra generated by single trace operators. For example, we can look at those for CFTR, then I call it MR. You can also do it for CFTL. Okay. Another claim is that now if you look at the single trace operator algebra, which is the one we should look at in the Largier limit, for the temperature sufficiently low, this is actually a type 1 von Neumann algebra. But for temperature greater than Hawking page, and then this becomes a type 3 one. Okay, this becomes type 3 one. And so here you can see clearly, again, there's some kind of state dependence here. Okay, because here the state is specified by your temperature. Okay, and so this is analog. So here the dependence is not so dramatic as this spin example. So therefore, every theta you actually have a different algebra. So here, just for greater than the Hawking page, they're all type 3 one. Yes.
If I picked two temperatures,
yeah,
above the Hawking page transition,
yeah,
I get two different algebras, or is it just the case that you can have two different algebra types for different states?
Yeah, you certainly get two different algebras, but they're all of the same type. Yeah, yeah. Yeah, the algebra itself always depends on the state. And it doesn't make sense to compare the algebra between the two states because they have different Hilbert space. Yeah. Yes?
I thought that you said in the last lecture the QFTs always have type 3-1.
Yeah.
Why is it now the CFT has type 1 and
Yeah, but this is the full CFT algebra.
Okay.
But only for the sub-region is type 3-1. Look at this full algebra of a quantum field theory is always type 1. Yeah, so type 1 algebra is the algebra which you can associate with the operator algebra on the Hilbert space. So when you have a Hilbert space, it's always type 1. So when you have a full quantum field theory algebra, it's always type 1. Yeah. So here we just look at the full CFT algebra and type 1. But now you look at the Largier limit, etc., and then now you have emergent type 3 one. Okay. And the same statement apply for ML. So I will not try to justify those statements here. It's a little bit technical to do them. Okay, it takes too much time. So let me just mention very quickly some of the supports. So one thing you can look at is the thermal spectral function of the single trace operators. So the basic idea is the following. Remember, we can classify type 3 algebras by looking at the spectrum of the modular operator. So here, since we have a thermal state, the modular operator is just given by your Hamiltonian. Okay, the difference of the Hamiltonian between the right and the left. Okay, so essentially, and then you just need to look at your the spectrum of your Hamiltonian, essentially restricted to the GNS Hilbert space here. Okay, to a GNS Hilbert here, and so that can be probed by looking at the 2-point functions, say spectrum of the 2-point function of single trace operators. Anyway, then you find that there's a discrete spectrum when t smaller than t Hawking page. And when t greater than t Hawking page, there's a continuous spectrum we support minus infinity to plus infinity. Okay, remember I mentioned yesterday for type 3, 3-1 algebra, the modular operator, the logarithm of the modular operator, they should have the continuous spectrum supported from minus infinity to plus infinity. So this is a strong indication that this is actually a type 3-1 algebra. And also you can show actually this theory, there's a half-sided modular inclusion and translation structure. So also I mentioned yesterday that this structure is unique to type 3-1. Okay, and again, so you can use this to justify it. And finally, so this is also required by the duality with the Bach. Okay, so now let me mention this last, let me now elaborate this last aspect in a little bit more detail. Okay, so now let's first review the Bach story. So the Bach story, you have a Fock space built on some vacuum. And for the black hole, if you want to be in the thermal equilibrium, you should be in the so-called Hartle-Hawking vacuum. Okay, so that's the one you built. And then you have the operator algebra in the right region and the operator algebra in the left region. Okay, so the M tilde R and M tilde L are the Bach operator algebra in the right and the left regions. Okay, so in the Bach you have an ordinary quantum field theory. So you can just look at the one Cauchy slice, and then to the right we call the M tilde R. To the left, we call the M tilde L, okay? And so M tilde R then is equivalent to the algebra for the full right, just from the causal structure, okay? And M tilde L is also equivalent to the full left, okay? So now the duality, now the statement of the duality is essentially that the J.S. Hilbert space on the boundary you build by acting single trace operators on the thermal field double state should be identified with the Fock space you find in the Bach. Okay, and then the single trace operator algebra on the right side is identified with operator algebra in the right quadrant of the black hole, and the left algebra in the single trace operator algebra is identified with operator algebra in the left of the black hole. Okay. And sometimes this is also called HKLL, and this has been studied much in the past. And so M tilde ML, they are, if you look at the quantum field theory in the full black hole space-time, and then this M tilde R and M tilde L just a sub-region, and so this should be type 3-1 von Neumann algebras. Okay. So then it's consistent that this MR and ML must also be type 3-1 von Neumann algebras. And so this is also required by consistency with the Bach. Okay. But we also have some independent boundary support. So emphasize that for single trace operator algebras, the operator at different times they are independent of each other. Okay. So that means when we talk about MR and ML, they're actually defined on the full boundary space-time. Okay, so MR and ML, they already include the information on the boundary of all time, okay, of all time. It's encoded in MR and ML. So now let's see this, so if I draw the boundary as say suppose this is spatial direction, this is the time direction, and the MR is defined for the full time. Okay, they're not independent. Okay, and similarly for the ML, but they are identified with the Bach operator algebra can be defined on a single time slice, because Bach you have ordinary quantum field theory. Okay. So it's the operator algebra for the all time actually mapped in the Bach to a full single time slice. So this makes sense because they have the same dimension. Okay, so this have D dimension, and this also have D dimension. Okay, also have D dimension. And I just want to emphasize that in principle, all the boundary time information is encoded in this mapping. Okay, encoded in this mapping. So now we want to understand, and also if you look at the operator, say a local operator in the right region, say at the point X in the right region of the black hole space-time, we should interpret it as an operator in the boundary space-time, in the boundary operator. Yeah, because these two algebra are identified. Okay, so this in principle is a boundary operator. So now our goal is, with this setup, we want to understand what is the future and the past region. Okay. And so let me just emphasize one point. By identification of those algebras, or probably we don't know whether the Bach region are connected or not. Okay, we just identify some operator algebra in the boundary with some operator algebra in the Bach. Okay, so we don't know whether they are actually in the Bach. Actually, they are. It's a connected space-time. Yes.
So you said if I consider the full quantum field theory algebra, it should be type 1, right?
Yeah.
But so if I just look at from the CFT side, wouldn't MR and ML just be type 1?
Yeah, but then in the large n limit, if you look at single trace operator, then they become type 3-1.
Oh.
Yeah, so that's the key non-trivial point here.
So only in the large n limit
Yeah.
become type 3-1.
Yeah, exactly. So at the finite n, it's always type 1. But now when you go to the large n limit, then become type 3-1. Even if it's defined for the full, yeah. And you have to define them for the full time, yeah. Right. Yes?
So if I consider just a subregion on the boundary and I take a subalgebra defining that subregion, does this duality still hold?
Yeah, it still holds. Yeah, that would be a different story. And you can also consider that story. Yeah, yeah. I will, if I have time, I will talk about that story. But unlikely I will have time. Yeah, yeah. That would be like part 4 or 5. Yeah. Anyway, so now let's ask, how do we understand the different notions of time in the Bach gravity? In particular, suppose we have this Cauchy slice in the Bach. Now, suppose I want to describe the evolution to some other Cauchy slice. How do I describe it using the boundary theory? Okay, in particular, I want this Cauchy slice to cross the horizon in the future region. Okay, so how do I describe in the boundary theory? So now from the Bach point of view, so Bach we have ordinary quantum field theory. Okay, so that means Bach you have ordinary causal structure. The causal, you can use the Heisenberg evolution in the Bach. So that means that the algebra on this slice and the algebra on that slice, they are completely equivalent. Okay, so from the Bach point of view, the algebra they are completely equivalent. So the relation between these algebra are just automorphisms. Okay, just act on automorphism on this algebra. So now if you remember, now the operator algebra on this single time slice are related to the U-ling of the MR and ML, okay? U-ling of the right and the left algebras. So that means that the Bach time will be evolution like this, just corresponding to the boundary automorphisms of MR and ML. Okay, because I already told you the boundary MR and ML already include all the boundary times. Okay, so the Bach time is essentially just some kind of automorphism of this algebra. Okay, so now the key questions we want to understand what automorphisms corresponding to the time evolution. Okay, so some of you may already ring a bell. Yeah, let me see. Oh, okay. Let me before that, let me just make one comment. So, okay. So now let's think about what are the most obvious boundary automorphisms. So the simplest one, say we have this boundary single trace operator algebra to the right and to left. So the simplest one is just consider the HR minus HL. Okay, so the HR, so H is the Hamiltonian. So the HR is the right Hamiltonian. And so that just gives you a standard modular evolution, and that's corresponding to the Schwarzschild time evolution in the Bach. So Schwarzschild time evolution in the Bach, you just do like this. Okay, if this time slice go to such a time slice, so it's always outside the horizon. We'll never take you inside the horizon. You say, okay, so how about let's do HR plus HL? Okay, so this is isometry. Okay, so this is isometry. So HR plus HL is no longer isometry. But if you act this on the operator, okay, if you take an operator here, if you act on HR, HL, it also will never take you behind the horizon. It's because the HL will commute with the operator on the right. So if you take the operator on the right, if you act by the evolution of this, always still remain in the right. Okay, we'll never take you to the future because the future involving some superposition of the left and the right. Okay, so this also won't work. And also this also have the problem, as I mentioned earlier. So the H have a dependence on N, and so actually this quantity is not quite well defined. So this is actually related to in the bulk. If you do the evolution here, there's some kind of kink here. Anyway, it doesn't matter. So now if you want to describe this kind of evolution, some kind of Cauchy slice which cross the horizon, so now this must be something emergent. Okay, it's not your ordinary evolution. Okay, emergent. In particular, since that the quantity in the future region involve both the left and the right degrees freedom, and in order to go to the future, the generator must involve non-trivial couplings between CFTR and CFTL. Okay, so just this kind of factorized evolution just will never work. Okay, will never work. They always have to the Bach-Kruskal-like evolution have to correspond into some kind of non-trivial couplings between these two. Okay, and then I will show that this emergent type 3-1 actually can give rise to this. Okay, can give rise to this emergent Kruskal time and sharp horizon, etc. Okay. So if we go back to this picture, actually just this picture here is fine. So now if you remember the Rindler story we talked about yesterday, so I mentioned that there's something called half-sided modular flow. And with half-sided modular flow, if you think this as a Rindler, if you know the Rindler right and the Rindler left, then you can construct the full Minkowski space-time. So here we just try to replicate that success here for the Rindler to the black hole, because black hole is like some kind of Rindler, okay? So we can, and now there should be some kind of half-sided modular flow we can use, then generate the future and the past region here, okay? So from the gravity side, it's kind of obvious, because locally near the horizon is it's just a Rindler, okay? So now but we want to give an intrinsic boundary description. So just to remind you, this story, this half-sided modular translation, you want to find the sub-algebra n of M, so that when you do the modular flow of M for half of the time, you remain in the algebra. Okay, you remain in the algebra. And if you have that, then that leads to a new generator with a generator which is bounded from below. Okay, and in particular, that evolution leaves your state invariant. Okay, so this can be used to generate new times. Okay. So now let me give you an example. So now let's consider. So remember let's remember the MR is the full operator algebra for all time. Now let's consider the sub-algebra corresponding to the time all the way running to t equal to 0. Okay, so this is sub-algebra. Okay, and this is only possible in the large n limit, because at infinite n, both n and m, they are equivalent to the operator algebra on the single Cauchy slice. Okay, but in the n equal to infinity, now they are distinct operator algebras, and n is a sub-algebra of it. And now also I mentioned that the modular flow for m is just a time translation, because it's a finite temperature state. And the time translation, of course, if you take the time, go to lactive, it still take n to itself. Okay, so this trivially satisfies this half-sided modular inclusion. And then that means now there must exist a G in this setup. Okay. And then now you can argue. Now you can argue that this operator algebra in the boundary below time 0 is actually equivalent to the Bach algebra in this wedge. Okay, so this is a t equal to 0 slice on the boundary, and you just draw causal light ray here, and intersect with the horizon, and then you find a wedge in tilde. and so this N tilde will be the Bach region and the dual to this region N on the boundary. And now you see this is almost identical to our Rindler story now. Okay, and the Rindler story, we choose such a subalgebra, and then you generate the law translation. Okay, so here is the similar scene. So if you choose such an algebra, and then you should generate some kind of a translation can take you to the future region. Okay. And okay, but now you can work out this explicitly. Okay, you can really work out the formulas. So yeah, you can actually work out this US. So if you take an operator in the right region, okay, if you take an operator in the right region, how much time do I have?
You have 18 minutes.
Oh, okay. So you take operator in the say take operator in the right region. Okay, so take an operator in the right region. So X here. Okay. So as we mentioned, because of identification, we can treat this as a boundary algebra. And now you can act with this half-sided modular translation evolution U to evolve this operator, okay, and then with parameter S. And then you find something interesting. So this is a calculation you can in principle do intrinsically on the boundary theory. Okay, I can construct this US. I can then just act on this. I can express this operator in terms of the boundary operators. I can just do it in the boundary theory. Okay, now you find there's something interesting here. So you find that there's a finite value S0. For S smaller than S0, this phi xs still belongs to CFTR. At the beginning, it belongs to CFTR because it's in the right region. But now, when you cross S equal to S0, now suddenly, degrees of freedom in the CFTL are generated in this evolution. Okay, just there's a sharp point S0, and then the degrees of freedom in the CFTL are generated in this evolution. Okay. And so this is precisely what you would expect to have a sharp horizon. So if you start with a point here, you evolve a little bit, you're still in the right region. But once you cross the horizon, and then you become causally connected with the left, then you must have the degree of freedom of the left CFTL. Okay? And so emphasize that this feature is highly non-trivial, okay, which is not possible if you have a type 1 algebra. Okay? Because naively, say this G, we say naively, if you just involve, say, something H plus HL, then this kind of thing will never, okay, will never generate anything of CFTL. Okay, we just never generate any CFTL. But if you take G to be generic couplings, say OR and OL, okay, plus something else. So if you take some generic coupling between OR and OL, then for any non-zero S, okay, even you start with the operator in CFTR, for any non-zero S, then CFTL operator will be generated. Okay, so here the non-trivial thing, which is unique to type 3.1, is that actually there's a finite interval. And that is required by this sharp causal structure. You have to have a finite interval S0. Okay. Anyway, so now you can ask, what is this S0? Okay, what is this S0? Okay. So now for the n I chose earlier, it turns out this S0 can be precisely give you the Kruskal evolution. Okay, so now let's use the suppose you have a Bach, you have a label this point using the Kruskal coordinates, say U0 and V0, and so this is now the horizon. Okay, so the U and the V axis are now the horizon, and so you label them by U0 and V0, and now you find out this S0 is exactly minus U0. Okay, so when you do the calculation, you don't use anything about the Kruskal coordinate, etc. So this Kruskal coordinate is purely emergent from the boundary theory calculation. Okay, it's emergent from boundary theory calculation. And in particular, so this evolution is in general non-local. So if you start with a local operator, this actually in general is a non-local operator. And but if this is close to the horizon, and then this just becomes a Kruskal law translation. And so this is expected from our Rindler story, because near the horizon it just becomes Rindler, and then below that in the Rindler this just becomes law translation. Okay, but if you're away from the horizon, then it's no longer exact Rindler, and this transformation becomes non-local. Okay, it becomes non-local. But nevertheless, you see a sharp S0. Okay, even though translation becomes non-local. But you can also do a little bit more finer probe of the causal structure. Now let's consider such a commutator. Let's take an operator, a local operator on the left patch, say take at the point x2. Okay, on the left patch. And now you start with a lot of operator on the right, and then you evolve it using this U. And then this evolution is non-local. But again, you find that this commutator is 0 when for some finite interval of S, but precisely when the S is equal to the Kruskal translation along the U direction to enter the light cone of this x2, and then this becomes non-zero. Okay, this becomes non-zero. Okay, again, this indicates that the causal structure. Okay, and so this is a final probe of the causal structure. Then yeah. Okay, so let me just also mention very quickly that in general the evolution is non-local, but surprisingly, if you take this operator dimension to be very large, the evolved operator dimension to be large. Large, I mean parametrically in order 1. Okay, never depend on n, and then you find actually the evolution actually become local. Okay, so this corresponding to the Bach field, the mass become very big. So in this limit, actually you find that the evolution become a local transformation. It takes you to a lot of points. And the transformation is given by the following formula. Okay, the details of this formula is not important. Yeah, let me just show you. And then it just involves, indeed, here now it's become a local flow. So you can actually draw a flow diagram. So if you start with this Cauchy slice, and then evolve to the future S, and then take you to Cauchy slice like that. Okay. And also you can choose n to be the upper half. So earlier we choose the n to be the t smaller than 0. You can also choose n to be greater than 0. And then that will be due to the Bach to this region. And then that will be generate corresponding to the Bach flow along the x minus, along this direction, along the v direction. Yeah, and then you get the flow patterns like this. Okay. So now you can, let me just mention, and now you can also compose the two. Okay, so this n give you 1g, and the earlier lower half n give you another g, and now you can add them together. Okay, remember if you add p plus and p minus, then you can generate just standard Minkowski time. If you take p plus minus p minus, you can also generate the spatial translation. Okay, so in principle with this you can generate everything here. Okay, and yeah. Okay, so let me just summarize. So the Bach time evolution related to the boundary automorphism, and then the internal time just generated by HR minus HL. This gives you the standard modular flow. And then if you want to see this kind of time, which can take you outside this region, and then you have to use this half-sided modular flow, which is specific to type 3.1. Okay, and then this can be used to generate the future and the past regions and the sharp structure, etc. Okay. So now let's summarize. So previously we have this identification. So now above the Hawking-Page transition, you have type 3.1. And then we show indeed, use half-sided modular flow, you can generate the full space-time. But if you have t smaller than the Hawking-Page transition, now you have type 1. type 1, then all this story don't exist, okay? So, and then you just have disconnected geometry. Okay, just have disconnected geometry. So this is perfect consistent with the story before. Okay. And so this gives you also precise way when somehow the Bach region should be connected. Okay, it should be connected. And so this is a more precise, say, characterization, say, than ER equal to EPR, than just entanglement itself. Okay, so this is a finer, just than the amount of entanglement itself. Okay, so this is a finer signature of the entanglement structure. Okay, so you need the specific type 3-1 structure to be connected. Okay, so I also mentioned that Witten has argued that if you include the 1-over-n corrections as a formal series, and then this type 3-1 structure then become type 2. Then using this cross product I mentioned yesterday. And also, also you can look at, say, the Sommerfeld double state in the macrocanonic ensemble. And I will not go into detail here. Let me just mention the result. That then now the operator, and now when you do the macrocanonic ensemble, and if the energy fluctuation of this macrocanonic ensemble is not large, if order 1, then you can actually include this Hamiltonian into the, anyway, you can again take some cross product, and then you can generate type 2 algebra for this macrocanonic ensemble, even in the Largier limit. Okay, to leading order in the Largier limit here, you can actually have a type 2 algebra. And then that can be used to generate the entropy, okay? And then, as we mentioned, the type 2 algebra gives you entropy, and then you can show that entropy is the same as the generalized entropy for black hole. And so this gives you explicitly that generalized entropy as an entanglement entropy, okay? As entanglement. Yeah, up to constant. Up to infinite space state independent constant. That's right. Yeah, it's the part induced by the matter. Yeah, the part. Yeah, you can include the area too, but it's only the part induced by the matter. The part induced by the falling matter. Good. So this provides the intrinsic Lorentzian understanding of generalized entropy, black hole as entanglement entropy. Anyway, and also there's some interest story in the JT gravity, which Pennington and Witten showed that in JT gravity, when you include all, when you treat it as a finite perturbative in G Newton, actually you also get type 2 algebra there. Okay, so now let me quickly describe how you describe other local Bach regions. So now let's consider safety in the vacuum. So now let's consider, so safety in the vacuum. So in the Bach, you just have a cylinder. You just have a cylinder. It's a solid cylinder, and the boundary series is a cylinder. The boundary series lives on the boundary of the solid cylinder. And now let's consider, so now imagine this is the boundary cylinder. This is, yeah. Now let's imagine you have a time band, okay, of the width T1, T2. And look at the operator in this region. Okay, look at the operator in this region. And again, this can give you some type 3-1 algebra in the Largier limit, you can argue. And now the claim, okay, again, I will not be able to go into detail here. The claim is that this operator algebra, which is the in the boundaries in this time band, then it's in the dual to the Bach region, which you send the light ray in. Okay, you should view this as spherical. Okay, so in this wedge, which I draw here, okay, equivalent to this the spherical wedge formed by the light ray. Okay, and so this is a cylinder, should be viewed as cylinder. Okay, and so the operator algebra in this time band then is dual to a Bach operator algebra in that region. And now let's look at, let's call this algebra A. And now let's look at the commutant of A. Okay, so let's look at the commutant of this time band algebra. Okay, so naively, if you in that finite n, then this is just the full operator algebra. The commutant will be trivial. Okay, but in the large n limit, actually the commutant is non-trivial. And then this should be dual to the commutant of this algebra in the bulk. And the commutant of the algebra in the bulk is precisely this diamond region. Okay, so now we have a way to describe the diamond region in the bulk. Okay, this diamond region does not touch the boundary. Okay, this interior diamond, just given by the commutant of this time band. Okay. So here, now I have to wave my hands now, okay? So now I want to argue, okay, here is only argue, okay, not show. Here I want to argue that the properties of this time, the lessons we learned from this internal black hole actually should be general. Okay, we can generalize that paradigm. In particular, the modular flow of Y. So now you have some boundary algebra Y dual to the equivalent to the operator algebra in this inside the region B. So now the modular flow of Y then can be interpreted as some kind of interior time inside the B. Of course, this time will in general be not local. Okay, but would be like, but still it's some kind of time. It's automorphism of the operator inside the diamond. Okay, behaves like some kind of time. And then the global time flow then can take you outside the B and then can be again described as some kind of half-sided modular flow. Okay? And then the causal structure then comes from non-analytic behavior under the half-sided modular flow. Okay. And in particular, if you give me the bulk geometry and give me the boundary algebra Y, in principle I can reconstruct this bulk region B, okay, whose algebra is equivalent to Y. Okay, good. So, okay, good. I'm also, I think I can be done. Okay, let me just, 2 minutes maybe, yeah. Good. So now as mentioned very beginning, as motivation, if you look at the diamond region in ADS, the local physics in that diamond region is not that different, okay, from the diamond in flat space, asymptotic flat space, or de Sitter. Okay, so if we understand how to describe it in ADS, that provides ideas how we may generalize that to flat space or de Sitter. So here, I just mentioned some discussion on the gravity side. So the understanding of this holographic distribution ADS for also understand for the de Sitter. So here I want to mention that on the gravity side, there have been some recent work by Chandrasekhar et al., which they argue that if you include some kind of static observer in de Sitter, then the operator algebra in the static patch is type 2-1. Okay, again, then that leads to a new understanding of the de Sitter entropy, say as some kind of entanglement entropy. Okay, so by combining this kind of a gravity story and the way we understand this causal diamond from the ADS, okay, so potentially we may be able to find some picture for de Sitter or flat space, the holographic distribution. Okay, so now let me just conclude. So I will skip the rest part. Let's see. Yeah, anyway, so let me just skip the rest part. Let me just conclude. Yeah. So just to summarize, yeah, very quick summary. So we give a framework for describing the emergence of local regions, different notions of times and the causal structure in the large N limit. Okay, and so we expect many qualitative features to survive at small but finite G Newton. But the key thing is that we need to develop a precise language. Somehow, when you go to finite G Newton, a small finite G Newton, somehow this qualitative picture should still be fine. But somehow, what thing you should change? And anyway, so currently we lack a precise language to talk about it. But hopefully, this operator algebra approach may provide such a language. Okay, so that's what we hope for. And also, I didn't mention this new insight on the entanglement wedge reconstruction. And so hopefully this may give you actually some first principle understanding where these islands come from. Okay, so also this may provide, Okay, I will just conclude here. Thank you. Yes?
So when you discuss the signature of the sharp horizon,
Yeah.
so we had a theory that was, let's say, equal to force of predominance lambda equal to 1.
Yeah.
Would we have the sharp horizon?
All right, yeah, that's a very good question. I should mention. Yeah, I forgot to mention. Right, yeah. So the question is So here we described. So I claim we can reconstruct the future and the Bach region from the boundary, and then when you cross the horizon, you have a sharp signature, and we know. So on the gravity side, we know there's a sharp signature in the classical gravity limit. Okay, but it's not known whether we have a sharp signature when you turn on the alpha prime corrections. So you still take the G string to be small, so there's no quantum fluctuations, but you turn on the stringy corrections. So whether the horizon is still sharp. Okay, so that answer, I don't know. But then the question, then you may ask, if you don't know the answer to this question, how do you know that actually you just claimed to did such a calculation? Okay, so my calculation, there must be some input from strong coupling. Indeed, so I cheated a little bit, okay, because I didn't have time to go to the detail. So when you construct this US, okay, so this thing is very hard to construct, okay, and but in the large N limit, from the constraint on this US, we can reduce to every property here. So you can see how this US acts on the operator. Okay, so we can reduce the action all the way to a phase, which we cannot determine. Okay, we cannot determine that phase. Okay, so you can write down explicitly how it acts on the operate on the boundary, but up to a phase, and that phase we have to use some trick to read it from the gravity side. And so that's the input from the gravity calculation and from that phase. And so once you put that phase, and then you see the sharp horizon structure. So of course, this phase will depend on lambda. Okay, so it's possible that when this phase structure change, when this phase change, maybe something can happen. Yeah. Okay.
Maybe in view of the time, let's say.
Yeah. Yeah. Yeah, so if you take lambda equal to 0, it's a little bit tricky. That's a little bit degenerate situation. So because of the energy level, strictly speaking, at the lambda equal to 0, all the energy level are quantized and finite spacing. But they have a huge degeneracy at some levels. Yeah, so I'm not sure. Yeah. It's a degenerate. Yeah.
This was Han's last lecture, so let's take the opportunity to thank you.
Yeah, thank you. for all the questions. Yeah. Mhm.
So for the subregion case, do you expect to like map the algebra in the causal wedge or the entanglement wedge? Because I know that like the entanglement